This video is part 3 of Chapter 12, Tests of Statistical Significance for PSY 222, Research Methods in the Psychological Sciences. Now we're going to move on from tests for comparing groups when you only have two groups or two time periods to data analysis where you have more than two conditions of the independent variable. Experiments frequently have more than two conditions. It's actually, pretty commonplace for us to have designs that involve that. In your semester project database, for example, when you use age as a categorical variable, you're actually given two choices in our database where you can have age divided up by 3 groups or age divided by 5 groups. So that's an example of an independent variable that has more than two conditions, either 3 or 5. In an experimental context, for example, a study that I did with looking at different kinds of media, I had one control condition where subjects watched an episode of When Weather Changed History, and then 2 experimental groups, one where they watched an episode of CSI with no mental health content in it, and the other experimental group where they watched an episode of CSI with mental health content in it. So we can have single factor experiments where you have one independent variable with 3 or more levels. There can also be complex designs, which we often call factorial designs, where you have 2 or more independent variables and you're looking for interactions among them. The type of statistic that we typically use to do the data analysis in these cases is called the analysis of variance. It is the most frequently used procedure when we do have an independent variable with more than 2 conditions. And you've gotten some experience with the ANOVA in your homework in Pallant. These tests do use the null hypothesis significance testing approach. Now the ANOVA for single factor independent groups designs, and unpack that, one independent variable, independent groups, meaning you have separate sets of people who define basically your separate groups. The ANOVA is basically an inferential stats test that allows you to determine whether your independent variable has a significant effect on your dependent variable or variables. If you look at the example that I gave you from the semester project, when I compared 3 age groups on optimism scores, life satisfaction scores, and perceived stress scores, you're conducting essentially an analysis of variance for comparing the 3 groups on each of those dependent variables separately. The logic is basically that you need to look at variation of 2 different kinds. You have error variation within each of your groups, and you have systematic variation that allows you to describe the differences across groups. The F test is the test that the significance test associated with ANOVA. And basically it's described statistically as a ratio of between groups variation. That's what we're referring to as systematic variation. A ratio between that and within group variation, which we're referring to as error variation. The results are reported, and you've seen this in your homework. The output can be really busy and hard to make inferences. If you just look at the output and try and figure it out without much coaching, and which is one of the benefits of having a book like Pallant to coach you through it, it can be very confusing. But one of the first things you're going to look for is what's called an omnibus F-test result. And basically that test just says, in this whole pile of means, all of these groups, is there a difference in there somewhere? And then if the answer is yes, you proceed and look for more detail about where those differences are. So this test, the analysis of variance, helps you to determine whether or not your independent variable has an effect. What you're going to look at, though, and it's extremely important that you kind of ground yourself in the descriptive statistics. You can't really, you shouldn't do an ANOVA and just rely on the F-test result. You really need to look at the pattern of data in the descriptive statistics before you can interpret what the outcomes mean, because the story really is in the means. We also need to remember that effect size matters. Over the last 15 years or so, there's been a steady increase in the number of researchers being expected to report effect size measures along with their ANOVA results. There are a couple of choices. You can use eta squared. You can also use a measure called Cohen's F. There's also a growing expectation that some estimate of power analysis be provided. And what I've always been told is that before data collection, you should do a power analysis and determine, based on the number of conditions that I have, what is the minimum amount of participants I need per group in order to feel confident in my findings. So power analysis helps you to do that. And that's why your authors are suggesting that you should conduct a power analysis prior to data collection to determine what's the probability of finding a significant effect based on varying levels of N. As Shaughnessy et al. Say, when you're comparing two means, you can then let me back up. When you're doing an ANOVA in a design where you have more than two groups, if you find that there are differences present somewhere, then you can make between groups comparisons two at a time. We often refer to them as post hoc tests, where we can then evaluate and determine where are the differences between the groups. So, for example, in my demo, where I looked at age in 3 groups and looked at differences in the dependent variables, what I found was overall significant F-test results. Then my job is to look at the pattern in the means and then to do post hoc tests and determine which among the 3 groups actually differ from each other. And I found that, for one of the dependent variables, that the youngest group differed from the oldest group, but didn't differ from the middle group, and the middle group didn't differ from the oldest group. So those are our paired comparisons. Now, to explore just a little bit further the 2 types of variation that are involved in the test, the F-test, you have error variation, or within groups variation, where you are looking, if you've done a random groups design, the only difference between your groups should be just the error variation, because you're randomly assigning them to groups. Now, if you have groups that are defined by individual differences, like age, sex, male versus female, then you also have, in addition to just regular old error variation, you also have variation that is attributed to individual differences. We would like to be able to hold conditions constant in order to decrease the level of error variation. Sometimes that's easier said than done. Now, the other type of variation in the analysis is systematic variation or between group variation. If you remember in your palette homework, the output is divided up. You have some rows in your output tables that go with each of these types of variation. And when we get to the point here in this part of the chapter where we talk about the output table, that will become even more evident. So systematic variation is where you're actually wanting to look at how different are these groups. And there's some error associated with that, but we're trying to isolate those systematic differences between the groups. But we want to factor in the amount of error that's associated with just regular old garden variety error as well as individual difference error. Now, if the null is false, then what you can do is you can infer that the independent variable has had some kind of effect on the dependent variable. You do need to look at the means and verify that, to your eye, how different do those means look? Because and what's the pattern? Which mean is higher than which other mean? And that helps you to kind of embed that significant finding into the real numbers that you have available to you. And one way that interpretation plays out is you should be able to then say these differences should be systematic. In other words, they should be interpretable in terms of the influence of the independent variable. Differences in means, this is our goal. We want there to be systematic error or systematic variability in the means based on hypothesized effects of the independent variable, but we do have to factor in the error variation that's associated with within groups error. So the F-test, what it does, it determines whether the variation, the systematic variation that we could attribute to the independent variable is bigger than what would be expected based on the contribution that error variation by itself would make. Now the concept of the F-test is defined in this way. You take the variability between groups and you divide it by the variability within groups, and that leaves you with an estimate of the size of the effect. The within or the between groups variability, that's what we describe as the systematic variation. And in the way that the test is statistically structured, mathematically structured, you have the between groups variation, systematic variation. You add to that the error variation. And then the variation, oh, I messed this up. I'm so sorry. I need to go back and fix this. This should say on the bottom here, variation within groups. I apologize. So the within groups error is just straight error variation. So when we actually kind of put the elements of the formula together, you've got systematic variation plus error variation divided by the error variation alone. And that produces the F statistic for us. Now, when we are going through the process of the F test, if the null hypothesis is true, there's not going to be systematic variation between the groups. And our inference would be that we're not seeing an effect of the independent variable in this case. And then, the expected value of the F test, if the null is true, is going to be 1, since the error variation divided by the error variation would equal 1. So if there's absolutely no effect, you're going to be left with an F-test value of 1. So, ultimately, the F-test, as it rises, gets greater and greater and greater than 1. That value becomes more likely to be declared significant. Now, just to give you an example of the single factor independent groups design, the research question could be, did the independent variable have an overall effect on performance on the dependent variable? The null would be that there's no differences between the groups. The overall analysis in the form of an omnibus F test would be examined. The null for that test would be that all of the population means, so you have a sample that you've pulled from a population, you're going to estimate, and that's part of what this statistic does, going to estimate what would the population mean be like. And the assumption you're going to make as the null hypothesis is that all the population means for these different groups are the same. Your hypothesis is going to be that one or more of these means is going to differ from the other means. In other words, there's a difference somewhere among the groups in their scores. So in the example of, I compared the 3 age groups on, say, life satisfaction, I would hypothesize that older individuals have higher life satisfaction than younger individuals, just for example. That would be my test hypothesis. Then I'm going to look at the means. So notice that I'm not running the test yet. I'm going to look at the means. And you may have noticed in some of my tutorials, I start with the descriptive statistics, and in your worksheet for the results section, I want you to describe the pattern of variable in the descriptive statistics before you do anything else. And then you look for visual evidence of an effect. Then you test it. So the next step after just visualizing the descriptives is to actually run the F-test. In other words, do the computations. And that's what we use SPSS for. Now, the first step in the null hypothesis significance testing with ANOVA is that you're going to assume no effect. The second step is you're going to compute the ANOVA F-tests and obtain your p-values for the F statistics. The third step, you're going to compare your p-value to your standard, which is you want your significance value to be less than 0.05. Now your authors give you an example, and I'm only giving you part of it. I'm showing you the table because I want you to go back to your chapter and read through the example again and make sure that you understand it. You're provided here in this sample output from SPSS, you're given various sums of squares which are associated with the different effects that you're wanting to look at. Group is the between subjects, error reflects the within subjects, and then a total sum of squares. You're given the degrees of freedom, which are based on your number of groups and your n. You're given the mean square values, and this is the calculated omnibus F. So the 7.0, and remember the null is 1, or the no effect, absolutely no effect is 1, and then the calculated p-value of 0.002. So to review, the summary table that SPSS provides you, and it's similar in other stats packages, it gives you statistics about the sources of variation in the data. You have mean squares for group, and that's referring to your independent variable. I sometimes call it a grouping variable. And that mean square is basically the systematic variation due to the independent variable plus the error variation. Then you're also given the estimate of error variation. It's referred to as the mean square error. The F-test, the way it's calculated behind the scenes, and using the numbers from the table on the previous slide, you have the mean square for the group divided by the mean square error, and that produces the value of F, because F is a ratio. Now, just to review, you have the results for the F test. And when we present this, what we present is the F, the degrees of freedom, the F value, and the P value. And then, we can look at that P, and in this case, the test result is significant at the 0.05 level. You can conclude that there is an effect for the IV on the DV. Now you have to explain where that effect is. So all we know based on this summary table is that there is a difference among the means, but the F test doesn't tell us which of the means differ. To figure that out, we have to take more steps. You can look at the confidence intervals to give you some idea of the pattern of the means. I like to look at a combination of confidence intervals where I'm looking at pairs. And I also like to look at the means plots because I'm a very visual learner and it helps me to just eyeball them. Eventually, I do want to do post hoc comparisons where I'm doing pairs of means to compare the groups. And that discloses for you among all of those groups, what are the differences that are driving the omnibus result. And that concludes part 3.